Okay, so we were given the model that represents carriers, infectious, and recoveries, also known as the CIR model, and it was used for predicting death rates for COVID-19 in Spain. My name is Hope.
My name is Reina.
And my name is Michaela.
Since the end of January 2020, COVID-19 has spread through Europe, generating a non-precedent medical collapse, firstly in Italy and secondly in Spain. Medical staff and services, especially intensive care units, mortuary services, sanitary suppliers, and others, appear undersized under the number of new patients and deceases per day. Current predictive models seem to have underestimated the rate of infection, and this new model predicts the evolution of infective diseases under uncertainty or low quality information, just as it has in happened under the initial scenario during the spread of COVID-19 in China and Europe. And it uses minimal input parameters. It is used to predict number of deaths and the number of demands for ICU beds. And this model also notes the date of infection for each individual. And there are two types. Type 1 is mild and type 2 is serious. And the CIR model, when compared to the SIR model, C stands for the number of carriers, whereas S stands for numbers of susceptible, I stands for number of infections, and I stands for infectious in the SIR model, and R stands for number of recoveries, and in the SIR model, R also stands for the number of recoveries. And the first equation we were given is h of delta t mu sub r dt, and this represents the probability of an individual to stop being contagious in time t after already living with the virus for a period of time, which is shown by delta t. And in this case, stopping being contagious means either reaching immunity or death. And when we consider the two types, mild as type 1 and serious as type 2 can either recover or die, and type 1 can only recover. And so our first equation represents the number of new infections of only type 1 at time t during the period of time dt. And type 2, or equation 2, represents the total number of new recoveries, either becoming immune or dying, from type 1 at time t during the time period of dt. And this long equation that we have is yielded when using equations 1 and 2 in relation to dr sub I of t, which gives the total number of new recoveries. And by definition, C sub I of t equals I sub I of t minus R sub I of t, represents the number of carriers, and this is found by subtracting the recoveries from the infections. And all of these equations are used for type 1 mild, but if we were to calculate these for type 2, you would have different numbers. And in summary, for the predictive model, the total number of carriers is found by C of t equals C1 of t plus C2 of t. And this is basically just adding the number of carriers for type 1 and type 2. And the total number of infections is found pretty much the same way. You're adding the number of infections for type 1 and type 2 in relation to time. And for the total number of recoveries, it is found the same way by adding the number of recoveries for type 1 and type 2 in relation to time.
So the contagion model is another part of the CIR model. New infections are proportional to the number of free carriers, which are carriers whose mobility has not been restricted. Alpha C sub 2 of T is the number of carriers who are isolated, and the number of infections is also proportional to the frequency that a carrier has of finding people who are also susceptible of being infected. In the propagation model, the average frequency omega, which is the average number of average number of people who an average person finds per day. The factor gamma features the average success of contagion, and the factor psi, which is the average fraction of infections that would be of type I, domain 1 to 2, where psi 2 equals 1 minus psi 1, and P is the total susceptible available population.
In the discussion portion of this paper, shown on the screen is an example of the model using data for the most plausible scenario, but it's noted that the real active cases for mild and serious cases has not been used to fit any of the parameters because the definitions are not necessarily clear and there are issues to be worked out within the definition themselves. Some of these there are regions which are not accessible to the contagion in Spain. The larger the time available to viral spreading, the larger the exposed population will be. And the initial date is assumed to be of March 3rd in this plausible case. Then additionally, there's a scenario 1 that is shown on the screen. This uses information where the first infection is on January 25th, and it includes all of the pieces from the equation that we explained earlier. This figure shows the spreading of COVID-19, assuming the less probable case. And on this graph, the solid lines are calculated using the CIR model also explained earlier, with data aligning with scenario 1 data. The difference in the number of final recoveries is huge. It's 13 million in the less probable cause and 0.28 million in the other case. A few questions that we had for the author after reading this paper was why the change from SIR to CIR? The majority of the variables stay the same, so we are curious as to why just the one variable changes. An additional question we had was, does a model similar to this work for a country other than Spain? And a follow-up question to that would be, how accurate would this said model be for a different country? And in conclusion, this model has shown that one set of parameters is required to obtain a prediction over a full curve. 2, a strong dependence between the date of the first infection and the susceptible population and risk reaction. 3, it can be used to estimate the number of susceptible people in near future massive infections. And finally, it can be used to estimate the demand for hospital service and the effect of governmental actions. These are all important factors to take into consideration when dealing with and preparing for an outbreak or a national pandemic such as COVID-19 that we are currently living in. Thank you.